All right, everybody, we are back. Um, and today we're going to be looking at lecture 12. And yeah, so we're going to be going over, kinetics of enzymes. Um, and yeah, this is going to be Michaelis-Menten stuff. And I'm not going to lie, they cover a lot of stuff in this, but I don't think all of it's very necessary. Um, so we'll see how long this takes, but let's go ahead and get into it. Good job on your exam. Your average is actually higher than ours by like a point or two. I think it's down here shown, but um, interesting. Nobody scored 100, which is normal, I'd say. A lot of high scoring people though, so that's cool. But yeah. So this is my exam when I took the class. Your guys was about a point higher in terms of average. The median was also a point higher. The standard deviation for ours was much wider, and we also did have a couple hundreds. I think what, three-ish. So yeah, I was about here. I was an 86 in this exam, so I was in this kind of section here, right? And just a reminder, I ended the class with a 3.9. Um, so just I think for you guys, if you want to end with around that GPA, I would say you should also be aiming for what I did, probably a point or two higher, honestly. Um, just because of how the exam is changing these days. I think let me actually do the math real quick for what my exam average was for you guys. So I had 86, 83, 87, and then 91. Divide that by 4. So yeah, so my average was an 86.75 for the exams. That was a 3.9. I would say probably try and go for like an 80, 88, 89, and you're probably either 3.9 or 4 of the class. If that's what you're looking for. So that's what you want. Probably around an 88 or an 89 for exam average. Um, okay, so there's a review of lecture 11. I already covered all this extensively, so if you want to cover that, go for it. But yeah, so let's go ahead and talk about rates. Why measure the rates? They just kind of it's just for the sake of defining complicated reactions and trying to understand how fast they go, um, and how does the addition of an enzyme actually change the speed at which a product is created, pretty much. Um, but yeah, I honestly don't think a lot of this is that important. I feel like you can read through it and you can get what they're talking about. All you really need to know for the exam is Michaelis-Menten and how it works. So just remember that this in the presence of an enzyme, and then you study the enzyme. Um, but yeah, and then you basically need some sort of signal. It's probably like fluorescence or something, proportional to like how much substrate or product that you have. Um, and usually it's like UV fluorescence, right? And you're basically trying to see how much substrate is changed per unit of time, or how much product is made per unit of time, right? But I wouldn't say this is super important for this lecture. It's just like for the principles of how we do what we do. Here's just an example of what you can trace. So in this case, they're measuring NADH from light absorbance. Um, Again, don't think it's that important for the exam, but this is just an example of how they measure product conversion, right? Right. So they're basically looking at the wave. They're basically shining this kind of light in and seeing how much of it is absorbed. And basically, um, if you get higher absorbance of this 340 nanometer, that means you know that you're making a lot of NADH, because NADH has that absorbance and not NAD plus. So how do we get these Michaelis-Menten curves, right? Um, Basically, you have a constant amount of enzyme and you have some amount of substrate, right? You have no product so far, none, because you just started the reaction, right? And you basically put this enzyme, you put this product in, and you're measuring the V naught, which is the slope of this line, right? Now, eventually, this slope will start doing this and plateau out. So you want to measure the initial velocity, because that's before the enzyme saturates, right? And that's what we care about. And they show that here, right? and it starts to plateau. Why? Well, one, you probably have a limited amount of substrate, right? Two, there's only so many enzymes that you have, right? So you only have a certain amount of enzymes, right? And once you fill all the enzymes up, right, you can't really you're kind of stuck with that until you actually make a product, and then you can fill another enzyme up, right? But eventually you run out of stuff, right? So that's the main idea there, right? So once S has been transformed, the rate goes to 0, right? Because if the whole idea is delta S, right, delta substrate, taking derivative here, right, of this, if this goes down to 0, right, then this divided by that is just 0, right? So that's why the product concentration, the slope here, is 0, right? Because you run out of substrate. And like I said, we measured this area here, just so we could have the initial velocity. We want the start of the route. We want to see how fast does this enzyme react initially when first put into the substrate, pretty much. And this is where they hit you with the boom, right? So you measure it. So you have a certain when you do this, right, you're at a certain substrate concentration, right? So this might be 10 millimolar, right? I don't know, not of product, but of substrate, right? Now you have to do this for every single concentration. So 10, 15, 20, 25, 30, 35, 40, right? And if you do that, you get these kinds of curves, right? So notice 7.5 micromolar, 1.0 micromolar, 0.2 micromolar. And we're measuring the initial rate. So that rate, that rate, that rate, right? And then we can use that to make this kind of plot. This is a Michaelis-Menten plot, right? That is a Michaelis-Menten plot. And you're basically taking these straight lines here that you take by taking the tangent from these lines, right? And you're using them to create this plot. So V naught, right? For V naught of 1 is here. V naught of 2 is here, right? V naught of 3 is here. Notice how the axis has changed from time to substrate concentration and from product concentration to initial velocity, right? A little bit different, right? That's because what we're doing is now we're basically taking these values, the concentration values that these different product concentration time changes, or these changes in product over time, were taken at, and we're now plotting them according to the concentration, right? And the initial velocity is just the slope, right? The slope is change in product for change in time, which is initial velocity, right? That is velocity, right? It's a change in some distance or some production per unit time. So that's what that is. Okay. So yeah, so like I said, new axes. So velocity, y-axis, velocity, y-axis, and then substrate on x-axis, right? And yeah, so no cooperativity is important. For Michaelis-Menten, there should be no cooperativity. And now here's the holy grail. Memorize this equation. I think you guys have it on your equation sheet, but just memorize it. Makes life a little bit faster, and you spend 15 seconds less staring at the equation sheet and more time actually doing the problem. Right? And the Km, right, by the way, is the concentration at which you reach half of Vmax. So this is Vmax up here, right? The Km, so this around here is half, right? The concentration there is Km, right? And the Vmax is just the maximum velocity, the point at which the thing starts to plateau out. So here's this equation again. K is the rate constant, so the speed of the reaction. They're not equilibrium. So equilibrium is KEQ, capital K. Very different, right? And so basically, right, for any enzyme substrate scheme, right, to make a product, you have different Ks. So you have the forward reaction, the reverse reaction, then from the enzyme substrate complex, you also have the forward and the reverse reaction, right? couple rules here from Michaelis-Menten. You don't have to derive the equation. I think that's extra. You don't need to. They never ask you on a test to derive the Michaelis-Menten equation. Okay, so, but it is important to know how this. It's very helpful to know how this works because it makes it so you don't have to memorize as much. So, right. So the first assumption, right? There's 5 assumptions for Michaelis-Menten. The first assumption is that product release is ridiculously fast and is basically reversible. So K2 is ridiculously large, and K negative 2 basically does not exist. So go away. Right. And these assumptions are important, right? Because Michaelis-Menten kinetics is basically a framework for how we look at enzymes. So it's not always true for every given enzyme, but under the Michaelis-Menten kinetics, we can apply these curves. As soon as we're out of Michaelis-Menten kinetics, we cannot apply them. Assumption 1 is that the substrate is in mass excess over the enzyme. So we want enzyme to be limiting, and the substrate is basically constant. So we basically want, what we basically mean by that is that we basically want this to be so high, right, that it doesn't really matter, right, how much you put in. It's gonna be ridiculously high. So I'm trying to think about if there's a better way of explaining that though. Basically, right, you want the initial velocity to be accurate. If you put too little substrate, right, you're not going to get the right initial velocity, and it'll skew your data, right, if the substrate is limiting. If the enzyme is limiting, right, then you're getting the max potential of the enzyme, right? Because if you have too much enzyme, right, eventually you'll saturate all the product, or saturate all the substrate, right? But if you have too much substrate, then all the enzymes will max out, right? And so that way you're getting data that's actually correct, because now you're actually going to the limit of the enzymes and not to the limit of the substrate, if that makes sense, right? Again, I'm gonna be honest with you. I don't feel like they don't usually test on these rules. If you want to know them, go ahead, and I recommend you probably do, because if you're taking the MCAT, for example, you'll need to keep them in mind at least. But for your exams, they don't really test on this. They might. I could see them asking a question on it, maybe, but I think there's other things they could ask you about on this exam, especially because you guys are going to start doing different sugar pathways soon. So, yeah. Right, so this is just another way if we're going through this again, right? This is all part of the these are all just part of the assumption 1. So assumption 2, right, is that when you initially start, there is no product. That makes sense, right? When you're just starting the reaction, there should be no product. And we say that because there should be no reverse reaction, right? And what that basically means is that that's why we can eliminate K negative 2, right? Because at the very start of a reaction, there is no product. And so you cannot go this way if you don't have all those things on the reactant side. In this case, the reactant side is this side. If you don't have any P, right, then you cannot go this way, and therefore K negative 2 is pretty much 0. Right? Right? Especially early in the reaction, because there's no product, right? And we're going to skip past all of this. Right, okay. So, steady state. Very confusing, I think, when you first look at it, but I think basically the idea is that we're in rapid equilibrium between this K1 and this K negative 1. So we're going back, that's not back, forward and backwards very quickly. And this is very slow. This direction here is quite slow. But that kind of tells you why it's steady state. So steady state is saying that the enzyme substrate complex does not change with time. And you may be wondering, like, what the heck do you mean? Well, what I mean is the speed at which you're actually making this complex is actually equal to the speed at which you're dissociating it. Right? The speed at which you're making the complex is the same as the speed at which you're dissociating it. So, right, we say steady state because it looks like you're at a constant enzyme substrate concentration, right? When in reality, you are actually making enzyme substrate and dissociating enzyme plus substrate. The enzyme, you actually just are dissociating the enzyme substrate complex, right? So that the rate at which you're dissociating it and also forming it are equal to each other and opposite. So therefore, it doesn't seem like there's any change, but there actually is. And again, we go into this, all of this stuff about that. And I'll talk about this a little bit later, actually, probably. Did we talk about it? Yeah, okay, yeah, so this right here. So, definition of Km, right? I do want to try and explain this. I think this is very easy to understand if you don't try and memorize it. So, I'm going to keep this here for my reference, right? But, basically, right, define Km. So Km, right, is the dissociation constant, right? And it's the point at which, it's the concentration at which you reach 1/2 Vmax, right? And this is very important, right, for when we start talking about inhibition, because Km changes, and Vmax is a little bit more intuitive, but Km is weird. So I want to talk about it now, just try and help you guys understand how it works. So Km, right, refers to the dissociation of the enzyme substrate complex. So dissociation of that. So dissociation of this, right? How do we dissociate the enzyme substrate complex? Well, this does not exist, right? So we can't, that's forming it, so I don't care about that. But two, it's too small anyways that it basically is non-existent. So the two ways we can dissociate the complex, right, are K-1 and K2, right? That's two ways we can dissociate the complex, right? And there's actually one way we can associate with this complex and make the complex, and that's K1, right? So when we start talking about inhibition, right, you're going to see me talking about, okay, well, if I add an inhibitor here and make this irreversible and do this, how does that affect these numbers? Right? So the way that they got this, right, is they just said, okay, the dissociation constant is going to be equal to the rate of dissociation divided by the rate of association. So the rate of dissociation is K-1, right, plus K2 divided by K1, which is formation. Okay? But back to this, right, they're going to start asking you about, oh, well, what happens to Km when it's competitively inhibited or uncompetitively inhibited or non-competitively inhibited, right? And you can use this scheme of just Le Chatelier's principle to figure that out. So for example, if I add a bunch of inhibitor, right, I'll go this way and I'll decrease my concentration of the enzyme substrate complex, right? Well, what is that going to do? That's going to shift this reaction and push it this way. which actually leads to more formation of the enzyme substrate complex, right? And since we're forming the enzyme substrate complex, we are increasing K1, right, which decreases Km, right? Do you see how I hope you see how I did that, right? I basically just used Le Chatelier's to go through how this works, right? And I'll go ahead and go through that again when we get down to the inhibition, which is a little bit lower down, right? But this is, I wanted to get this out of the way now so that you can kind of understand what I'm talking about, right? And yeah, they basically go on this massive tangent about how they calculate it. If you're interested in this, feel free, but not important for the not important for the exam, I don't think. They never tested us on this, and they shouldn't test you on it. Right? So this equation, something to memorize. Right? And here's a nice little slide, right, that shows you all 5 rules. I know it starts with 0 for some reason, but all 5 rules, right, for McCallum's and kinetics. And here is that equation. I think the other equation you should know, and I think they mentioned it, is the Kcat of the enzyme times the enzyme concentration, right, equals Vmax. That's the other equation you should know. So this equation up here and this equation you should know. Right, and this is important as well. So KD is not the same as KM, right? So KD, right, it's just like protein plus substrate goes into protein substrate, right? There's no like third like production, right? Like there is with enzymes. And enzymes, you go from this enzyme plus substrate to the complex, and you make a product, right? But there's no, with proteins that are like binding proteins like hemoglobin, there isn't like this K2 doesn't exist, right? Because you're not turning it into something else, right? Oh, and here we go. They actually do talk about the Kcat here. I kind of forgot about this. Yeah. So here's that equation again, right? This equation is just this, but rearranged, right? The Kcat is the turnover number. It's basically a frequency, right? It's basically it's a unit of like 1 per second or 1 per time, right? It's like how many things are you producing per unit time, right? So like for example, 500 over second. So 500 500 things produced per second, right? So this is a nice little number. It basically tells you the speed at which the enzyme does things. So you can also think about it like this, right? So like it would be basically the Vmax, right, would basically be some sort of concentration, so like some C value, right, per unit time, right? That should be delta actually. Be delta, right? Some change per unit time, right? And Kcat, right, would be some value of change in concentration, right, per enzyme, per times time, basically, right? And you're basically multiplying that by enzyme concentration, right? Right. And so basically what happens is this and this cancel out, and you're left with the change in concentration over change in time, right? Hopefully that makes sense. But basically the idea is that the Kcat is basically some sort of, it basically tells you how much production a single enzyme can do per unit time, right? Which is why you can multiply it and say that Vmax equals Kcat times times E. Right? all there is to it. And I want to make sure this is clear. Km is not the same as Kcat. They're different things. So Km is not Kcat. Kcat has to do with the catalysis of the reaction. Like, so can the enzyme actually react the substrate turn into product? Km is binding affinity. Can the enzyme bind the substrate? Very different things, right? They will ask you on exams. I guarantee you they'll ask you on an exam. They'll give you some sort of like active site complex or like some protein, and they'll tell you about the different amino acids on it, and they'll be like, oh, does changing this affect Km or Kcat? Right? Stuff like that. They'll, like, for example, if they change, I don't know, an aspartate that's involved with like some acid base reaction, right? That changes Kcat, but does not change Km because it's not involved with binding. It's involved with the actual reaction, right? Some are actually involved with both, right? And they'll usually specify that, right? But just be aware that they do like to ask weird questions like that. And catalytic efficiency, right, is basically just this idea of how good is the enzyme at catalyzing the reaction and holding on to its substrate to make product, right? So you can imagine, right, that if I increase the Kcat or decrease the Km, aka make the binding affinity stronger, right, then the catalytic efficiency will be much higher, which makes sense, right? If I bind my substrate strongly and I'm actually able to catalyze quickly, then I will be a way more efficient enzyme, right? So now we can talk about inhibition, right? So we've got different types of inhibitors, right? We've got competitive inhibitors, you've got uncompetitive inhibitors, you've got non-competitive inhibitors, all sorts of stuff. So if malate, I think it's like malate, but not malate, serves as an inhibitor for succinate dehydrogenase, which is this enzyme you will learn about for citric acid cycle. But what you should be able to tell me is that these structures are so similar. One carbon difference, right? If a structure looks similar to the normal substrate, it's probably a competitive inhibitor. Not always the case, but probably is, right? So a lot of drugs, right, are, you know, the inhibitors, right? They inhibit things, right? All that stuff, right? Yeah, and they can be reversible or irreversible. So it's either reversible, non-covalent, or irreversible, covalent. There are some exceptions to this, but this is generally true. If it's irreversible, it's generally a covalent bond, right? I can't, just to be clear, these inhibitors down here are not covalent. There might be a way you can make them covalent, but I personally have never seen them as covalent. So let's go ahead and talk about competitive inhibitors first, right? So the idea is, right, and actually, yeah, the first thing we should actually define is probably this. So Ki, right? So Ki is the dissociation constant for the inhibitor, right? So basically, you know, you add an inhibitor, right? You want to know how much of the inhibitor is actually taking up the enzyme, basically, right? So basically, the lower, right? Think about it, the lower this Ki is, the higher this EI is, which means you're producing a lot of enzyme plus inhibitor, right? Which means that you're driving this reaction this way, right? So something to keep in mind. That's how Ki works, right? So for competitive inhibitors, right, the inhibitor binds to the substrate. The inhibitor binds to the enzyme instead of the substrate, right? So it binds to the enzyme, right? instead of the substrate. And what does that do? Well, if I have a very large or very small Ki, right, that means that I have a lot of this, right, which means that I will be producing a lot of the enzyme plus inhibitor, right? So what does that do? Well, let's think about this, right? If I do this, right, I'm decreasing the amount of enzyme, right? And how do we replenish that enzyme? Using Le Chatelier's, we can say that my enzyme and substrate will dissociate, right, to form more enzyme, right? So let's think about that. What does that mean in terms of our little schematic? Do I have that image, right? Let's think about this, right? This little schematic, right? So I'm basically saying that this number, that we're increasing the K negative one, right? And what is Km equal to? Km is equal to K negative 1, K 2 divided by K1, right? And we're increasing this value. So Km goes up, right? I hope you can see my thought process here, right? I'm using Le Chatelier's. I'm not memorizing it. I'm using Le Chatelier's to tell me what's going to happen, right? So Km goes up because K negative 1 goes up, and K negative 1 goes up because when I add this inhibitor, right, I end up going down this way, right? And that depletes the number of enzyme, which ends up shifting this to the left, right? Now let's think about Vmax, right? Well, Vmax is the maximum rate of the enzyme, right? Well, how does that work? So if that's the maximum rate of the enzyme, right? Let's take a scenario, right? Let's say that I add a bunch of substrate, right? So I have some inhibitor, right? I have some substrate, right? If I add the same amount of inhibitor and substrate, the probability of you running to a substrate or running into an inhibitor is about the same, right? Now let's think about it. What if I add 10 billion substrates and then one inhibitor, right? The chance of you actually finding the inhibitor is pretty dang low, right? So the chance of you finding the substrate is much higher. And so what that means, right, is that if I add enough substrate, right, the enzyme will just keep picking up the substrate and converting it into product. So Vmax actually does not change, right? So we have a couple things here. So Km and Vmax. Hopefully that makes sense. So Vmax stays the same, and Km actually increases. This is what you need to know for competitive inhibitors, right? I hope that makes sense, right? If we add enough substrate, right, it doesn't matter how much, if I add a couple inhibitors, right, because I'm just going to delete all of them. Well, not delete all of them, but the probability of you finding the inhibitor, if you add a lot of substrate, is practically zero, right, or close to zero, or very, very small, right? So the idea is that if I oversaturate with substrate, it doesn't matter how much inhibitor I add, right? The amount of the maximum velocity is going to be kept the same because I can't find the inhibitor, so the inhibitor is not doing anything, right? Hopefully that makes sense. And here we go. Km increase, but not Vmax, right? And this whole alpha term, right? You actually need to be able to calculate this. I don't know if they give you the equation for that. Yeah, so this is alpha, right? Alpha is defined here, right? Basically, how much concentration of inhibitor do you have, right? Divided by that dissociation constant, right? And in this case, right, because we just said, right, that Km actually increases, right, when you add, for a competitive inhibitor, you multiply Km by alpha, right? Because alpha is telling you how much the Km is changing, right? And well, alpha basically tells you how the enzyme is changing in response to this inhibition, right? And since it's a competitive inhibitor, right, the alpha only affects Km and not Vmax, right? You'll see that in different cases when we do uncompetitive inhibitors, it actually affects both. But the way that it does it is actually different, right? So because it's an increase, right, we multiply Km by alpha because Km increases with competitive inhibition. And Vmax stays the same and is not affected, so it's not multiplied by alpha, right? And here's some examples, right? I wouldn't worry too much about this, but basically, right, if you have no inhibitor, right, this is basically how it works without alpha, right? If you have no inhibitor, this is 0, and 0 divided by 0, or 0 divided by some number, 0 plus 1 is just 1, right? So alpha is just equal to 1, right? Uncompetitive. Okay, let's do the same exercise, right, with uncompetitive inhibition. Let me grab. So, what the heck is box? Hello? Why is there a box? Drawing. So, if I bring this here, right, do my little scheme again, right? So, we've got reversible inhibition again, right? But this time, right, we're adding uncompetitive inhibition. So uncompetitive inhibitors, they bind to the enzyme substrate complex. So only bind enzyme substrate complex. So they bind here, right? So we're adding an inhibitor right here, right? Let's think about what happens, right? So Km, right, is going to be this idea of K negative 1 plus K2, right, divided by K1. Right? If I add inhibitor here, right, what happens? This will shift this way, right, to produce this enzyme substrate inhibitor complex, right? And in order to replenish this, right, this will shift this way, right? And remember how we're specifically defining Km. Km is specifically defined as K negative 1 plus K2 divided by K1. Right? It's pretty bad K, but lowercase k, right, equals Km. Right? If I increase, so this has no bearing on Km right now because it affects it in a different way using alpha, right? That's not in the equation for Km, right? This, however, is. That is K1. If I increase K1, right, this whole thing decreases and Km goes down, right? That's the big thing here. Km decreases in uncompetitive inhibition. What about Vmax? What about Vmax, right? Well, this is different from competitive inhibition, right? So with competitive inhibition, right, I could add a billion substrates, right? And eventually, if I had an inhibitor, right, the probability of finding the inhibitor would be very low, right? This is different, right? Because now the inhibitor is binding to this and stopping it from going here. So it doesn't matter if I add 8 billion substrates, right? It's just going to get inhibited, right? As soon as it gets to this stage, right? So if we have inhibitor, right, and we add a billion substrates and we get to this point and it just inhibits it, you can imagine that we just kind of get stuck with a bunch of this, right? Especially if Ki is small, right? If Ki is small, right, that means that this is large, right? That means that it's producing a lot of this. So you can imagine, right, that if we have a lot of if we have a lot of inhibitor, right, that has in the Ki is small, right, then you end up producing a lot of this guy, right, and so you basically never produce any product, right. So because we're making this enzyme substrate complex stuck, right, we're getting it stuck in this inhibitor form, right. It's not covalent, remember, but it is stuck in that form, right. That means that we inadvertently decrease the amount of enzyme we have available to us, right? Because we're getting it stuck in this form. So if you remember how a Vmax works, Vmax, draw it somewhere, Vmax equals Kcat times enzyme, right? You're basically decreasing the amount of enzyme, right? Not really, like you're not actually removing enzyme, right? But because the inhibitor is blocking it, you're actually decreasing the apparent number of enzymes you actually have. So Vmax actually goes down, right? And you'll see that with alpha, right? So same as before, alpha, it's alpha prime in this case, but same thing, right? Because both Km and Vmax are decreasing, we actually divide them, right? So remember with competitive, we multiplied because it was increasing, right? We multiplied, right? Now that we're using, now because we're decreasing both of them, right? We divide, right? Right? We divide Vmax and we divide Km by alpha, right? And for mixed inhibition, right? Uh Mixed inhibition is interesting because it's kind of a mix of both, right? So it might bind here, it might bind here, right? Some inhibitors more strongly bind to the enzyme substrate complex than just the enzyme, right? So it depends, right? But there's still like constants for that, right? There's constants for forming the enzyme inhibitor. There's constants for forming the enzyme plus the enzyme substrate inhibitor, right? Different constants, right? And basically, right, what happens is, generally speaking, I believe Vmax generally stays the same. Um, but in this case, it actually decreases, right? Sorry, no, Vmax stays the same, but the Km is the one that's a bit weird. The Km can either increase or decrease, right? So because with mixed inhibitors, there's even a little bit of it making this complex, this enzyme substrate inhibitor complex, like with the uncompetitive, right? You're gonna decrease the Vmax, right? Because you are blocking out this substrate, right? You are blocking out this enzyme, right? So it can't actually do its job, right? So because of that uncompetitive inhibition, right? That uncompetitive inhibition like aspect, there is a decrease in Vmax always, right? Km is a bit different though, right? For that, I would say like I'm trying to see what they did here because this is a bit interesting. Uh oh. Oh, I see what they did. Yeah, so I think yes, this it's kind of written weirdly. Generally speaking, right, I will say they usually don't test you on this. It could show up, very possible, but I feel like they usually test you on competitive and uncompetitive and not mixed. But the idea here is right the same. So for Vmax, right, because Vmax is always decreasing, right, regardless, you multiply it like normal, right? For what's it called? for Km, right, it's either increasing or decreasing, right? Uh, so the way that you basically get around that, right, is I believe you can just you can do what they've done here, right, and use this formula, right, this one up here, right, or rewrite it as this, right? It's the same thing, right? You could do that, and basically the way this works is there's a little bit of algebra cancellation here, and if you do this, you end up with this, right? If you do the algebra for it and you try and cancel it, I won't go through that because I think it's a little bit of a waste of time. But basically, for mixed inhibitors, right? It could be an increase or a decrease depending on which alpha is stronger, if that makes sense, right? So like in this case, right, with this whole like alpha km alpha naught thing, right? Alpha prime, sorry, right? If the competitive aspect is stronger, right, it'll increase and km will go up. If the uncompetitive aspect is stronger, this will increase and it'll be km will go down, right? But because it's like a mix of the two, right, you can't be sure. So you should use this equation here, right? For Vmax, it doesn't matter because Vmax is only affected by the uncompetitive aspect, and it's always just A prime in that case. But because Km is affected by both, right, you need to make sure that you're taking both into account when you're doing the math. I hope that makes sense. It's a bit confusing, but hopefully that makes some sense. And here's a nice table of how it works. If you just want to memorize it, go for it. I wouldn't recommend just memorizing it. Try to understand how it works because they could ask you questions on how it works. But here if you want it, right? Non-competitive is also a thing. In this one, Vmax actually stays the same and Km doesn't change. You need to know this for the MCAT, but you don't have to know it for this class, I don't think. I don't believe they test you on it, and they didn't test us on it when I took the class either. Yeah, here's a summary. It was a bit of a longer one today. I hope that was helpful though. I want to make sure you guys understand how this works because this is definitely one of the harder parts of exam 2. But yeah, I hope it was helpful, and thank you for watching.